Is particle physics only about particles? This is the question which we'll address in this lecture. We will give an overview of the building blocks of universe as per our current understanding. No mathematics will be done, only a very brief introduction. We will mention certain things regarding nature of force and nature of elementary particles, their interaction and properties in this lecture, which we will describe in details in future lectures. Anyone who goes through a physics course is tormented by two terms. One is particle, the other one is wave. In some experiments, particle aspect of observed entity is spoken of. In some other experiments, the wave aspect of observed entity is spoken of. And we then try to impose a duality character on the observed entity. At the end of this lecture, we will see that there is another way of looking at things in a theory which is called quantum field theory, which has gained much ground. Things might appear to be spectacular, weird, or even spooky. But yes, this is all about investigation of ourselves, realization of ourselves and our nature, done in the subject called physics. So let us start. Let us speak of two very important interactions in physics. One is pair production, the other one is pair annihilation. In the phenomena of pair production, a photon impinges on a nucleus and gives rise to matter. So this is materialization of energy, where radiation is converted into mass. Here a positron and an electron is produced when photon strikes a nucleus, and from conservation of energy it follows that the photon should possess at least 1.02 MeV of energy for this interaction to occur. And from momentum conservation, it can be shown that a nucleus has to be present, because a photon cannot disintegrate while traveling in vacuum. It has to retain its speed c always. We will not go into details, but this is just the phenomena which we mention of. Another phenomena which is opposite of this one is pair annihilation, which represents irradiation of energy, that is creation of energy from matter according to Einstein's E equal to mc square, where a positron and a electron, which are particle-antiparticle pair, they meet and the interaction is violent because none is there after the interaction, only energy is there. So this is called pair annihilation. In particle physics experiments, particles with given energy and momentum, they collide, they interact. So we have an initial state which comprises of certain particles with certain energies and momentum. But after collision or after interaction, we have, or we may have, a different set of particles with different energy, different momentum. So this is the final state. So what has been emphasized here is, in various experiments of particle physics, the initial state and the final state are widely different. Particles are different, their numbers are different, their energies, momenta, all are different. And this occurs through creation of particles, annihilation of particles. A proton-proton collision at relativistic energies more particles come out than those went in, like pions, heavy particles, and so on. Let us bring quantum ideas into discussion briefly. First, Einstein's photon theory. If light falls on a metal, electrons are emitted. It was observed that photoelectric emission occurs only if frequency of light is above a cutoff or a threshold, denoted by nu zero in this diagram. Now with wave picture of light, this could not be explained, and Einstein proposed his photon theory, according to which light is built out of a stream of particles called photons, each having energy h nu, where h is the Planck's constant and nu is the frequency of light. Now when h nu falls on an electron sitting in a level, it is able to take it out if it is sufficiently energetic. And this is the famous Einstein's photoelectric equation. Now, if we equate the expression of energy as given in photon theory equal to h nu with the one E equal to mc square, which was a famous outcome of special theory of relativity also of Einstein, then we end up with the kinetic mass to be h nu by c square. And from another relation of special theory of relativity, which connects energy of a particle with momentum of the particle and its rest mass, if we put rest mass of photon to be 0, then what we get is this relation. So P equal to h by lambda. Now Dubroy extended this idea to matter also. Matter means particles with which matter is built, suppose electron, proton, etc. For them, this relation holds as per Dubroy's hypothesis, where p is the momentum of the particle and lambda is the associated wavelength as per his theory. And we can recast it in terms of their kinetic energy so that we get this relation. And there are two relations actually. One holds for non-relativistic particle and the other one for relativistic particles. These are not matter of discussion here, but the essence is that according to the Dubroy theory, a particle is associated with a wave, and if the dimension of the particle is smaller than the associated wavelength, then particle character will get suppressed and wave character will manifest, and particle behavior will be dominant if dimension of the particle is greater than the associated Dubroy wavelength. Now this Dubroy hypothesis was confirmed when electron beam produced interference pattern, diffraction pattern in some of the famous experiments performed by Davison, Jarmar, G.P. Thompson and others, which conclusively showed that electron beam can be treated as a wave in these experiments. So what we get is wave particle duality. In some experiments they show wave behavior, and in some other experiments they show particle behavior. Now the task is to integrate the ideas of wave, which is an extension in space, to the idea of particle, which is localization in space. Particles are associated with waves through the Dubroy relation lambda equal to h by p, and the particle character, which is localized in nature, is associated to the wave character which is extended in nature by the Heisenberg uncertainty relation delta x delta p greater than or equal to h cross by 2. In essence, if a particle is localized at say x0, that is delta x equal to 0, there is no uncertainty regarding its location, then as per quantum mechanics we have to attach to the particle an infinite number of waves. Again, if we think that we will get on with a single wave of certain wavelength lambda 0, that is delta lambda equal to 0, no uncertainty in wavelength, which in turn means that from this relation there is no uncertainty in p momentum, so delta p is also 0. This means that the particle's position is infinitely uncertain. It can be anywhere between minus infinity to plus infinity. So comes the wave packet description, where we say that we have to superpose waves of various lambdas to build a wave packet, and particle stays within the wave packet, and wave packet group velocity travels with the particle velocity. In other words, wave packet does not leave the particle, or particle does not leave the wave packet. So wave packet along with it carries the particle, and particle may be anywhere within this wave packet, and the uncertainty thereby in x and in p, because we have superposed large number of waves to build this wave packet, these two uncertainties, one in x and one in p, is related by Heisenberg's uncertainty relation. This psi, which is also called matter wave, has a special significance, that its square, that is mod square, represents position probability density of finding the particle at position x, or in 3D case at position vector r at a time t. We are not going into these things. And lastly, this psi should be such that the total probability as calculated from this probability density is unity. Till now we spoke of how particles are tied to waves, or waves associated with particles, through a clever ploy or judicious use of certain relations like Einstein's photon hypothesis, the Broglie hypothesis, Heisenberg's uncertainty relation, etc. We now bring in another idea, and a very old one of 1845, introduced by Faraday. Waves are associated with fields. Nature is made up of fields. Let us give a few examples to illustrate this point. For instance, if a heater is on at a place, we have different values of temperature at different points, at different times throughout the region. Take the case of gravitational field. Earth moves around the sun being in its gravitational field. Let us consider a charge q, and it has its influence that extends up to infinity. As we know that Coulomb's law is of infinite range. Consider a current carrying wire and the famous Ørsted's experiment performed in 1820, in which the influence of some field called magnetic field was clearly evident through a deflection of the magnetic needle when current was sent. Also, we can think of magnets. A north pole, in spite of being separated, responds differently to another north pole or south pole. And there are plenty of other examples. Also, for charges in motion, things are described by Maxwell's equation, which describe an electromagnetic field, and we say that electromagnetic field or the signal or the electromagnetic wave propagates with speed of light, which is also a wave whose value is 3 into 10 to the power 8 meter per second in vacuum. So we can conclude that field lines are unreal, imaginary, but what they represent is very real. They stand for some force of interaction which is real. Let us list down certain properties of field that struck us hopefully in this discussion. Field is a property of space and time, as field varies from point to point as well as from time to time. Field is spread everywhere, as it has a value very near to the source as well as far away from it, even at infinity. So field behaves like a fluid. Consider an ocean and suppose we are in it. Ocean is everywhere. It just extends, it just spreads, fills the entire universe. Again, fields vary, and a variation that is favorite to us all is the sinusoidal oscillation or variation. As we know, sinusoidal oscillation happens very commonly or widely, for instance in the case of electromagnetic field, where electric field oscillates, magnetic field oscillates as well. Another important characteristic of field is that field carries energy. Electric field has this amount of energy per unit volume, magnetic field has this one, electromagnetic field has what is called field energy, which consists of an electric part and a magnetic part. Also, we can think of field momentum in an electromagnetic field, where S is a Poynting vector given by this expression, and this represents energy flow per second per unit area. Now, what about energy distribution? If we rely on wave picture, we know that energy is distributed continuously over wavefronts. On the other hand, if we rely on particle picture, energy is discrete. It is parceled into indivisible units. And electromagnetic field is made up of photons. Till now, we have popped up ideas from here and there, and we have to stitch them together to get to what we call quantum field theory. Now, what are the ideas we have put up? Idea of particle, idea of wave, idea of field, idea of energy, idea of quantization, idea of creation and annihilation of particles. What we have to do is we have to cobble them up and present a theory. This lecture, as mentioned at the very outset, discusses the building blocks of the universe. What are the possible or prospective candidates? One is the particles and the other is the waves. Now wave is associated with field and particles can be created or annihilated. Now all these have been discussed a while ago. Now we have to stitch in energy, we have to put in energy into the description, and will not bring into mathematics into the depiction of things for fear that it would spoil everything. But before proceeding further, let me mention that without mathematics or complex calculations involving mathematics, we cannot inch further. So what we describe or are trying to describe is just a crude way of getting to the bottom and then giving a shallow view of things. In spite of crudeness or lack of rigor, we just present things which will build a rough idea, keeping math at bay regarding the building blocks of the universe. Now it is a combination of quantum mechanics, classical field theory, and special theory of relativity, and this gives us the quantum field theory, the basic ideas of which are as follows. There is nothing called particles. Ultimately, the fundamental nature of the universe is that it is filled with fields that can be perturbed, that can vibrate, oscillate, and experience excitations. Every particle has its own field, and the field carries chunks of energy. The field is fluid-like. It extends all the universe. Now the energy, that chunks of energy, is determined by the rest mass of the particles. For instance, there is nothing called electron particle, but the universe is filled with a fluid-like field called electron field. The field can be excited by an energy greater than or equal to 0.51 MeV, which is the rest mass of electron, or rather rest energy of electron. So if electron field that pervades all space is excited by energy of 0.51 MeV, then electron will be produced. This electron that is produced is a tiny ripple in the underlying electron field that is modulated by a particle. Similarly, there is a quark field, a fluid-like field extending or pervading all the universe, and a small vibration or excitation or perturbation produces a ripple called, say, up quark. So particles are ripples or waves or excitations or perturbations of the field. This holds for all particles, and we will soon show that the universe is filled with 17 different fields corresponding to 17 particles. Let us now describe what we mean by quantum vacuum. What happens if we have no particles? No particles mean a vacuum which we guess is presence of nothing or absence of everything. Here everything means particle. So vacuum is absence of particle, but it is not absence of field. So fields exist and they always do. And there are oscillations of field that may be calm and tame, or may be wild, bubbling or frothing. This is called quantum vacuum fluctuation. It is like the 0-point oscillation that follows from Heisenberg's uncertainty relation. So vacuum is alive with fields, and even there is possibility of creation and annihilation resulting to emptiness. You are giving me a gift and taking it away at the same time. All particles are excitations or ripples of the same underlying field, just as two waves of an ocean, they belong to the same underlying ocean. One field can excite the other field. So an electron field can excite a quark field, or a quark field can excite an electron field, and so on and so forth. Next, how does a particle send signal to another particle? That is, how does two particles communicate? It is the same technique followed through which someone in a river can communicate with the banks of a river. If we drop a stone in the river, then ripples are created locally, and the waves generated travel fast to the banks and hit the banks at some location, that is locally. Here too, if a field is affected locally, then disturbance can propagate and affect a distant point, and this is a local disturbance at the distant point. We can also explain pair annihilation as follows. Particles and antiparticles are excitations in the same field, but excitations are equal and opposite. So we have two opposing waves that annihilate each other, like two waves smashing at each other in antiphase, and the result is that we have no wave after the smashing. Production of particles can also be explained. Proton and neutron are made up of three quarks. Neutron is made up of UDD and proton is made up of UUD. So energy of a quark field of neutron can be transferred to, firstly, the quark field of proton, and the excitation appears as a proton. Secondly, to the electron field, and the excitation appears as an electron. And thirdly, to the electron antineutrino field, and the excitation appears as an electron antineutrino. Electron-electron repulsion, which is an interaction between two particles, can also be explained. Electron has a field, and photon also has a field in the same region. Now electron field vibrates at 2 points, and these excitations are two electrons. The electron field causes vibration in the photon field. An excitation of the photon field generates a virtual photon. So two electrons can communicate by generating excitation in the photon field, and the result is a repulsion. Let us mention a few facts. Fields are real entities, but they are not made of any real substance. Fields exist in space and have energy, they carry energy, contain energy, and property of field can be calculated and accurately predicted. But this field theory does not give any explanation regarding dark energy, Big Bang, matter-antimatter disparity, and so on. Let us now come back to the question, is light a particle or a wave? They are waves. A particle is just a ripple in the field. It is what manifests when one measures a wave. So the fundamental nature of universe that we have mentioned right now are not particles but fields. Let us try to understand why field is a better idea than particles. The ultimate aim is to describe interactions and evolutions. Interaction between two particles is difficult to explain. Firstly, they interact, that is attract or repel in case of charged particles, even though there is a separation between them. So this is an action at a distance interaction. Now action at a distance is not meaningful. Also, they interact through an exchange of quanta. This is also a questionable thing. Since how does an electron know another electron is sitting? How does the sun control Earth's movement from a distance of 1 astronomical unit, notwithstanding the fact that gravitational interaction is very, very weak? Einstein's general theory of relativity addressed this problem and eliminated the idea of action at a distance by replacing space with space-time field, which is a field that pervades reality, and according to it, gravity is due to bending of the field of space. Let us show the building blocks of the universe. There are 17 fields or quantized waves. 17 particles have been shown. Each has a field, which are quantized waves or comprise of chunks of energy, and ripples represent manifestations of the particles. Electron, neutrino, muon, neutrino, tau, neutrino. This constitute the lepton family. Up quark, down quark, strange quark, charm quark, bottom quark and top quark constitute the quark family, and they are called fermions. They constitute matter, and hence this field is called matter field also. The force carriers are the bosons, and this is the Higgs boson. When Higgs field ripples, we see particles, and there is gluon field, which describes strong interaction, photon field, which describe electromagnetic interaction, Z boson and W boson, they represent weak interaction. These are bosons or force carriers. So they make up 17 quantized fields, and these are the elementary particles suggested by Standard Model. Space-time is also a field, but it is not incorporated in quantum field theory. Graviton, that is thought to describe gravity, is still elusive. Now, if it is incorporated, it would be the 18th one. Presently, universe is thought to be a combination of 17 fields, or so to say 17 massive oceans interlocked and dancing in harmony. Before ending, let us just give a hint of what mathematics is done here. We spoke of excitation, fluctuation that needs creation and annihilation of particles or quanta. And one way to mathematically generate a quantum field is to use harmonic oscillator. Consider a string in which several oscillators or oscillating particles having energy En are moving, and the associated waves correspond to m modes of oscillation. So we have to deal with a collection of harmonic oscillators moving with allowable frequencies that generate the quantum field, where particles pop in and pop out. Let us end with a note that it was a crude description intended to convey the current understanding about the building blocks of the universe. Finally, let us address the question that we started with. Is particle physics all about particles? The answer will be, it is all about fields. Let us end with two quotes. One is of Martin Gardner, a popular writer, who says that the formulas of physics are compressed descriptions of nature's weird repetitions. And the other is of Donald Rumsfeld, who was US Secretary of Defense. There are known unknowns, but there are also unknown unknowns. That sums up many things. Thank you.